Welcome to your podcast for Lesson 47, Circular Motion. After watching the podcast, you should be able to describe and explain centripetal acceleration and force. Okay, the warm-up question. You have a merry-go-round that has a radius of 6 meters, and we know it makes a full rotation every 5 seconds. And we're asked to determine the speed of the horse on the outer edge of the ride. Well, what you have to remember is as that horse makes that trip around, okay, the distance that horse is going to travel is going to be the circumference of the circle. So we can use our velocity equation, v equals d over t, but remember that the circumference of the circle is going to be equal to 2 pi r. Okay, which we can then plug into our equation for the distance. So v equals 2 pi r over t. Okay. So 2 times 3.14 times our radius, which was 6 meters, divided by our time of 5 seconds. Okay. So when I plug and chug this, I'm going to get 7.5 meters per second. For objects that are moving in a circle, we say they experience tangential velocity, meaning that their velocity is always going to be tangent to the circle, or in other words, it's always going to be perpendicular to the radius. So you can see on the diagram that that velocity is making a right angle with the radius of that circle. When we do problems, we'll see objects that are either rotating or revolving, and it's important to know the difference between them. Rotation is an object that spins around a point located within itself. So we know the Earth rotates on its axis, and we know that it does this once every 24 hours. It's our day. Revolution is when an object moves in a circle around some point in space, and it's outside of that object. So, for example, the Earth revolves around the Sun, and we know this takes 1 year or 365 days. Remember, Newton's first law tells us that an object in motion will stay in motion in a straight line unless acted on by an outside force. So if we're dealing with circular motion, that means there has to be some force acting on an object that causes it to move in a circle. That force is known as centripetal force. Okay? It's called centripetal because centripetal means center seeking. So if I were whirling a ball on a string, and let's just say it's moving in that direction, okay, there would have to be some force applied to that ball to keep it from moving off in this straight line, right? That force is going to be our centripetal force, which is going to be pointed directly towards the center. And again, this would be its tangential velocity. Notice how that would make a right angle to the radius of the circle. The radius of the circle then is our centripetal force. So if this is a rock that's being whirled on a string, that centripetal force is going to be the tension, for example, in that string. Okay. Remember that acceleration is any time an object speeds up, slows down, or changes directions. So it can be moving at a constant speed, but if it's turning or changing directions, then it's accelerating. So if an object is moving in a circle, it's constantly changing direction and therefore constantly accelerating. That centripetal force is going to be what causes the object to accelerate towards the center of the circle. What keeps it from moving towards the center of the circle, though, is, again, Newton's first law, saying that it wants to stay in motion in a straight line. So that tangential velocity prevents the object from going straight towards the center. For example, we know the moon revolves around the Earth, but even though there's a centripetal force pulling it in that circular path around the Earth, we don't worry about the moon crashing into the Earth because it has that tangential velocity which is going to prevent it from moving towards the center of its path. So when we draw a centripetal acceleration, we know again, centripetal means center seeking, so it's going to have that acceleration towards the center of the circle, and what prevents it from accelerating or moving in that direction, rather, is the fact that its tangential velocity is perpendicular to the radius of the circle. Okay, so there's two equations that you can add to your formula card. For centripetal acceleration, we know that A is equal to V squared divided by R. And for centripetal force, we say Fc is equal to M times V squared over R. Or sometimes you'll just see it written like that. Same thing mathematically. We can also use this equation for something we're going to learn in the next lesson called centrifugal force. Okay, so in this problem, you have a runner moving at a speed of 8.8 meters per second who's rounding a bend with a radius of 25 meters. What is the centripetal acceleration of the runner? Okay, well, we're going to use A equals V squared over R. Okay. Our velocity was 8.8 meters per second. And I have to square that. And that's divided by the radius of 25 meters. Okay? So 8.8 squared divided by 25 is going to give us 3.10. Okay? The units are going to be meters per second squared. If you're wondering how we get that, notice on the top we have meters per second squared. So it would look like this. And then on the bottom we have meters. And so one of the meters would cancel out, leaving you with meters per second squared. All right, in this problem we have an airplane traveling at 201 meters per second and it's going to make a turn. We need to solve for the smallest radius of the circular path that the pilot can make and keep the centripetal acceleration under 5 meters per second squared. But notice we need to solve for this in kilometers. So we're going to start with one of our new equations again, A equals V squared over R, and I'm going to rearrange this to solve for R, right? So R would move up here and A would move down here. They just kind of swap places. Okay, so R is V squared divided by A. Okay. Now our velocity was 201 meters per second. Okay, square that. Divided by the most we know we want the acceleration to be is 5 meters per second squared. So we're going to plug that in as our max value. Okay. And when you plug and chug this into the calculator, you're going to get 8,082 or 8,080.2, sorry, meters. But we want this in kilometers. So remember, when we're going from meters to kilometers, we need to divide by 1,000, okay, which moves your decimal 3 places to the left. Okay, so we're going to end up with 8.08 kilometers. Okay, problem number 4. We have a 45-kilogram merry-go-round worker standing on the ride's platform 6.3 meters from the center. If her speed as she goes around the circle is 4.1 meters per second, what is the force of friction necessary to keep her from falling off the platform? Okay, so what we have to understand here is that if this is the path that the merry-go-round is taking, and this is her standing, let's say on the edge, 6.3 meters from the center, we know that there's going to be some centripetal force pulling her in, and we'll call that FCP for centripetal force, and we know that that thing that's providing the centripetal force here has to be the force of friction. Okay? So we can say that the force of friction is equal to our centripetal force. I can now substitute in our new equation. So the force of friction, which provides the centripetal force in this problem, is going to be mv squared divided by r. So our mass of this worker is 45 kilograms. Make sure when you're solving these problems that mass is always in kilograms. The velocity is 4.1 meters per second. And again, square that. Divided by a radius of 6.3 meters. Okay? Plug and chug this into your calculator, and you end up getting a force of friction equal to 120.07. And units, kilogram times meters per second, and those units squared. One of the meters is going to cancel out, so kilogram times meter per second squared is going to give us a Newton. Okay, in problem number 5, you have a car racing on a flat track at 22 meters per second, rounding a curve with a radius of 86 meters. Two things that we've defined here. First, the centripetal acceleration of the car, and then the minimum coefficient of static friction needed between the tires and the road so that the car does not skid out when it's turning. So for the first part, the centripetal acceleration, we know we're going to use A equals v squared over r. Our velocity in this problem is 22 meters per second divided by a radius of 56 meters. Okay. And when you plug and chug, you're going to get 8.64 meters per second squared. Okay. The second part of the problem, solving for the coefficient of static friction, we need to remember, that's a bad S there we go, coefficient of static friction. We need to remember that in order for that to be true, the frictional force has to equal the centripetal force. Okay, so I'm going to substitute in mv squared r for the centripetal force. And if you remember our equation from the last set of units, we know that frictional force is equal to mu times F of n. Okay, now we know that in this case, as the car is going around the track, the car right here, gravity is going to be pulling it down, and there's no net force in the y direction, so that means that Fn has to be equal to Fw. And I know that Fw is equal to mg, so I can substitute this in here for Fn. Okay, so I end up with mu times mg equals mv squared over r. Okay. Now I have mass on each side, so I can cancel that out. And I need to solve for mu, so I'm just going to divide each side by g. Okay, so mu is equal to our velocity, 22 meters per second. And that's squared, divided by the radius, 56 meters, okay, times our value of g, which is 10 meters per second squared. Okay. And when you plug and chug this into the calculator, you are going to get 0.86. Remember, there are no units for coefficient of static friction.